Okay, in this question we have a pellet pushed up against the spring and then released, goes around the loop, stays on the track. You're asked to neglect friction to start with, and to work out the smallest deflection of the spring for which the mass has enough speed to go all the way to the top of the loop without falling off. So we have to consider the case at the top of the loop, D. We're going to consider the case where it just loses contact with the surface, and at the point where it loses contact with the surface, its reaction force, so the surface force on the object, is going to be zero. So equating the forces in the normal direction at D, we're going to have mg, the weight, is equal to the circular motion, m times an, so mv squared over rho. So the speed that it needs to just stay in contact here, so v min, is going to be 2.215 meters per second. So then we need to work out, neglecting friction, how much displacement of the spring is required so that it ends up with, at point D, with the velocity 2.215. So we apply the energy balance equation, so the kinetic energy plus the initial potential energy due to gravity, potential energy due to the spring, is equal to the final kinetic energy, final gravitational potential, and the final spring potential. Now, we know that it starts from rest, so that's 0. We know the final velocity, because that's as a function of the v min. So our final kinetic energy is a function of v min squared. We know that we choose our datum to be 0 at A, so our initial potential energy, or potential, is 0. And our final spring potential, after it's fully extended, is 0. So what we're left with is that the spring potential energy should be equal to the sum of the final kinetic energy plus the gravitational potential. So the gravitational potential is mg times h, so h is 1 in this example, so this is just g upon 2 joules, and the energy due to the spring is half k delta x squared, and given that it's compressed from its fully decompressed state, we know that we only need to find the delta x in order to find x2, or the compression distance. So since we know what k is, we have the expression for the initial potential of the spring, and equating it all together, we can get our formula as a function of delta x, and we can work out that it should be just under 8 centimeters of compression for the spring.